Welcome to this presentation about optimizing blockchain security with an AI coach via computationally adaptive modeling. Blockchain operates as a decentralized tamper-proof ledger by organizing validated transactions into timestamp blocks, each cryptographically linked to its predecessor. In the picture is shown how blockchain operates in a simple way. So first, new data is entered into the blockchain. Then a block representing this data is created. The block is then broadcasted to all the nodes in the blockchain network. Each node, so each participant, chooses to approve or deny the new block. If approved, the new block is added to the chain permanently. So when a transaction is broadcasted, nodes verify digital signatures, account balances, and protocol compliance before reaching consensus via mechanisms like proof of work or proof of stake, ensuring that any attempt to alter past data would require economically impractical collusion across most network participants. Nevertheless, blockchain remains vulnerable to subtle anomalies, sudden surges in high-value transfers, or like repetitive microtransactions that deviate high from normal patterns, consensus delays, or unexpected forks that may signal double-spend attacks. Delays in block confirmation can reveal consensus manipulation, in example selfish mining, while unexpected forks often signal double-spend attempts. In the 2016 DAO exploit, a re-entrancy bug let attackers drain funds repeatedly, prompting a hard fork. Blockchain also endured 51% attacks, as seen on Ethereum Classic 2019. Blockchain can also suffer from node or key compromises and large-scale DDoS outage that enable fraudulent transaction or halt production. Smart contract flaws, from logic errors to record manipulation, remain a major cause of large-scale asset loss. In a security operations center, analysts must process hundreds or even thousands of alerts per hour. Studies of Giudetti et al. Demonstrate that vigilance begins to decline sharply after just 15 to 20 minutes of continuous monitoring, greatly increasing the chance of missed or misprioritized alerts. Even a brief moment of inattention can cause network intrusions to go unnoticed or delay incident responses, jeopardizing the integrity of the blockchain. Integrating AI supports can reduce this vigilance decrease by continuous monitoring and employees' workload, adaptively highlighting critical alerts. Network design. At the left, we have the multi-level network picture, which has three different planes. First, we have the pink plane, which is the base level. We have the blue plane, which is the higher level. And we have the purple plane, which is the second higher level. In the pink plane, we see two circles and some outside world states. First, we have at the bottom left a circle which contains the employee mental states. These are 28 states representing the employee's cognition, arranged in 6 categories. We have sensor as S states, representation SRS states, belief BS states, preparation PS states, execution ES states, deviation feedback DEF states. Then we have at the top left, we have some outside world states which are not encircled in the pink plane. Then we have like the context states, the CS states, and the world states, the VS states. And we have some fatigue states which feed into the W states in the blue panel. Then we have at the bottom right corner, we have some other outside world states. These are the world result VR states. We have at the top right, we have a circle which contains the AI model states. These are a parallel set of the employee's mental states for the AI coach, which mirror each human sensor, representation, belief, preparation, execution, and deviation states. In the blue panel, we have W states. These monitor their two connected states and use Hebbian-style learning to adjust first-order connection weights. We have WAI states. WAI states stay constantly at 1 to indicate that whenever both connected nodes are active, the link is fully ready to strengthen without itself ever changing. Then we have in the blue panel also some monitoring states, M states. These detects when a human model states and its an AI model prediction differs beyond a set threshold, emitting an error signal. Then we have in the purple panel, we have the WW states. These regulate the learning rate of their parent W states, controlling how fast first-order weights adapt in response to detected errors. All these states are represented in the MB base connectivity matrix. This is a matrix where a 1 indicates a directed causal link and NaN indicates no link. Then we have the MCV connection weights matrix, the same shape as MB, assigning each existing link a numerical weight. Larger values mean stronger causal influence. Then we have the MCFV matrix, which has the combination function weights. This is a matrix indicating which functions to apply to each state's inputs. Then we have the MCFP combination function parameters. This is a matrix that configure the chosen function's shape as input. In example, the logistic threshold S and steepness R. Then we have the MS speed vectors. These inputs control how fast each node moves towards its target activation. And we have the initial values, the IV. This is a matrix which contains a value at which a state starts. Now we will discuss the context and world states. Each context state feeds directly into the corresponding VS states. So first we have the CS new transaction. This represents context pulse whenever a new blockchain transaction arrives. Then we have the CS smart contract execution. This is a context pulse whenever a smart contract execution event occurs. Then we have the CS consensus delay, context pulse whenever consensus round is delayed. Then we have the CS node down, context pulse whenever a blockchain node goes offline. Then we have the CS privilege attempt, context pulse whenever an authorized access attempt is detected. And we have the CS blockchain fork, context pulse whenever a chain split fork is detected. And now their corresponding world states. We have the WS new transaction, a new blockchain transaction arrives. So we have the VS smart contract execution, a smart contract execution event. We have the VS consensus delays, consensus round is delayed. With the WS node down, a blockchain node becomes unreachable. VS privilege attempt, an authorized access attempt. And we have the VS blockchain fork, a chain split fork is detected. And now we will discuss the sensor representation and belief states, which are all mental states. First, we have the SS detect anomaly. TX employee detects anonymous transaction pattern. Then we have the SS detect contract issues, sensor flags unexpected contract behavior. We have the SS detect node issue, which represents sensor node communication failures. We have the SS detect policy mismatch, which represents deviation monitoring from policy rules. Then we have the representation states, the SRS TX risk level, numeric risk estimates of the current TX. We have SRS contract risk scores for a smart contract event. We have the SRS node trust score, trust level computed for a node. We have the SRS policy compliance, which represents the degree of compliance with policy. Then we have some belief states, like the BS threat urgency, belief in how urgent the threat is. We have the BS system reliability, belief in overall blockchain integrity, and we have the BS accountability awareness, which is the belief in traceability and auditability. Now we have some other mental states, preparation and execution. The preparation states include PS alert security team, which prepares to alert the security team, a PS block user or node, which is a mental state to prepare the revoke user node access, PS request system audit, prepare to trigger a blockchain audit, PS ignore and monitor, prepare to monitor further without action, PS finalize block, prepare to finalize add the new block to the chain. Then we have execution states, ES send alert, send a security alert, ES revoke access right, ES log the incident in the system, and ES finalize block, finalize and append the validated block to the blockchain. At last, for the base level, we have deviation states, which is a mental state, and finalization states, which are the outside world states. First, we have the dev policy deviation, and deviation from policy was confirmed. We have dev repeated failure, a recurring deviation pattern detected, dev action mismatch, executed action that not match preparation, and the world finalization states, VR alert broadcast the security alert to wider network system, VR access revoked, enforce the access revocation action on the implicated user or node, VR incident logged, record the incident details into the system's audit log, VR aggregated response, aggregate the results of all executed actions into the global system state, and we have VR block finalize and append the validated block to the blockchain. This figure shows simulation of the base level states with the AI coach disabled. Once fatigue is introduced between steps 1200 and 1800, clear behavioral declines occur. Initially, before fatigue is introduced, the state dynamics of the uncoached model resemble similarly behavior of the coached model. The agent learns the routine responses to blockchain events in the early learning phase. However, as fatigue increases, a collapse in several key state dynamics occurs. Crucial belief states x21 to x23, which previously hovered around 0.9, declined towards 0.3, 0.4 during the fatigue period. This indicates that the employee's confidence in the system's integrity and threat awareness decreases sharply. Decision-making also declines. Preparation states for security actions falter or shut down. For instance, the model often fails to proceed with block finalization or alerting actions when fatigue peaks. In the PS state panel, the normally active decision states drop to near zero, reflecting the fact that the agent's default to inaction, in example, ignore and monitor, becomes the prevailing choice rather than executing a necessary alert. This leads to visible consequences in the outcome level variables. The execution, the result states, x36 till x40, show that the critical actions such as incident logging and blocking finalizations were not maintained. They drop out fast, indicating missed or undone tasks. Without the AI coach, the employee's internal model exhibits prolonged deviations. This figure shows higher level and context-related states with the AI coach enabled. The top panel shows again the same kind of states with the x97 in dashed black. The W states, which encode connection strengths in the mental network, remain relatively stable, showing only a slight dip during the high fatigue period, before quickly recovering. The decision-related states also largely sustain their values. For instance, the intention to finalize new block fluctuates only midly with fatigue, staying well above the 0.8. The influence of the AI coach is clearly visible in the lower panels. The monitoring states show peaks in the early stages. This is because the W states have not yet fully learned. Then the M states briefly show a peak at the onset of fatigue, indicating that performance losses have been detected. The WW states show similarly activity. So even during the fatigue interval, the AI-supported model continues to learn and relearn appropriately, stopping fatigue from having a significant impact on the employee's cognitive state. A what-if analysis was conducted to evaluate how the employee's perception of threat urgency state X21 changes under different system conditions and decision thresholds. 3 effectors were adjusted to specific low and high settings. The speed of X33, which determines how quickly anomaly cues influence human judgment, the threshold of X17, which defines the transaction risk level that triggers escalating concerns, the threshold of X65, which regulates the translation of estimated risk into perceived urgency. Threat urgency was sampled at 4 time points, at T is 350, 1500, 1750 and 2000, across all 8 combinations of these settings under 2 conditions, with AI coach support and without AI coach support. Each factor is weighted according to its operational impact: minor 2, moderate 5, serious 7, or critical 9. The risk contribution of each factor is calculated by multiplying its probability by its impact, and these contributions are then summed to produce a single overall risk score combining likelihood and severity. Without AI coach support, threat urgency is driven entirely by thresholds. A low X17 threshold pushes urgency above 0.85 by T is 350. Peaks near 1 at T is 1750 and remains above 0.96 by T is 2000. Raising X17 drives urgency below 0.35, nearly 0 at T is 1500, before recovering to 0.74, 0.88 by T is 2000. Changing X65 further suppresses and delays urgency by 0.2 till 0.3, while doubling speed changes urgency by less than 0.001. In this human-only model, the critical threshold is always violated, and the moderate advisory threshold fails in 40% of the cases, yielding risk contributions of 0.8, 2, 2.8 and 9, for an aggregated risk of 14.6, which is a 94% higher than with AI coaching, underscoring the danger of unassisted fatigue-driven decision-making. With AI coaching, urgency starts near 0.6 at T is 350, almost double the lowest of values, and rises above 0.96 by T is 1500. And reaching 0.999 by T is 1750, and settling around 0.96 till 0.97 by T is 2000. Threshold changes alter urgency by less than 0.005, so only the earliest 0.7 threshold is breached in 40% of runs. Risk is 0.8, while all more severe boundaries hold, yielding an aggregated risk of just 0.8 and demonstrating consistently high vigilance. So in conclusion, applying an AI coaching model to blockchain security monitoring extended and enhanced employee response strategies. Under the coach's guidance, incidents were detected faster, false alarms decreased, and overall vulnerability after suspicious events dropped significantly. By continuously reinforcing effective actions, overall security effectiveness improved, leading to fewer undetected attacks and a lighter employee workload.